Carrying on with our angle theorems. So the next one's about cyclic quads. So the opposite angles in a cyclic quadrilateral are always supplementary. So there's our picture. A cyclic quadrilateral, remember, is one where its vertices all lie on the same circle. So in this case, alpha and beta would add up to be 180. So if I was going to use that, ABC plus ADC, simply that. Opposite angles in a cyclic quadrilateral equals 180. Let's go and prove it. I'm just going to join up the other two vertices to the centre of the circle. And then I'm going to use our idea from yesterday, the angle at the centre being twice the angle at the circumference. So I can say angle AOC would be twice alpha. But if I look at the reflex angle AOC, so the bigger one, then it would be twice beta. But I know both of them are going to add up to be 360 because it'll be a revolution. So 2 alpha plus 2 beta is 360. Therefore, alpha plus beta is 180. And thus proving our result. The other cyclic quad theorem, which is a bit like the exterior angle of a triangle, people often forget this one and it can save a bit of time. So an exterior angle is always equal to the opposite interior angle. So here's our picture, there we are. So DCX would equal BAD. It's easy enough to prove. I don't know that I did bother proving it in the notes, did I? Because simply we'd say, well look, these two add up to 180, because opposite angles in a cyclic quad. These two add up to 180, because of an angle in a straight line, so therefore they've got to be the same size. And so that's why this is useful, that you don't have to do those two steps. You can just go straight to saying, oh, well, the exterior angle is equal to the opposite interior angle. Okay. Now, let's do this one. Angles subtended at the circumference by the same or equal arcs, or of course it would be chords, because again, remember, endpoints of a chord or an arc are the same 2 points, so they could subtend to a third point, are equal, which is a mouthful. So I tend to just write angles in the same segment, because if you imagine the chord there, we're saying if the two angles end up in the same segment of the circle, then they're going to be equal. So I'm going to prove ABD is the same as ACD. Again, I'll join A and D up to the centre of the circle. And then I can say, well, look, AOD is twice ABD. Again, using that theorem. Angle at the centre twice the angle at the circumference. But then I can say, well, look, AOD would also be twice angle ACD. So therefore, ABD is the same as ACD. Okay. 9C we'll add to our list of exercises to do